Good evening, everybody. My name is Jerry Liu. I am an 11th grader at the Bridgewater Raritan High School. Welcome to another fun math workshop, and today our topic is the shoelace formula. So as an introduction or as some type of warm-up, you guys can just calculate the area of this square shown in the graph below, the square UVWX. And when you're done, please put your answer in the chat. Okay, so as you can see, this is a square and each side length is 9. For example, if you look at vertex x, you see the x-coordinate of this vertex is 5. And if you look at u, you would see that the x-coordinate for u is in fact -4. So you would thus conclude that the length of side ux is 9. So the area of a square is the square of the side of the length. So you have 9 squared equals to 81. Now, this seems pretty simple, right? It's just the area of a basic figure in the coordinate system. But obviously, not all types of shapes are as simple as a square, and you find much more difficult ones to try to calculate the area of. For example, take a look at this figure. It is neither a normal pentagon, nor is it a normal quadrilateral, or any type of polygon where you have a general area for, you have a general formula for the area. So in such a case, how would you find the area of this polygon? So how we do this is by a set of steps that is called the Shoelace Algorithm. So the first step is to list the coordinates counterclockwise. So in this case, we know that this polygon has 5 vertices. So we could start from, for example, P1, and we could just list the coordinates counterclockwise. So starting from P1, we list 3, 4. We list them as separate numbers like so. For P5, you would do 5, 6. And then for P4, you would do 8, 5. For P3, it is 12, 8. And we can end it with P2 on 5, 11.
Why is P4 8, 5, not 9, 5?
Oh, whoops. That was just a mistake on my part. It's a bit blocked from where I'm seeing it, so I read that as 9. But thank you for the correction. It's 9, 5. So our next step after listing the coordinates is to repeat actually the first one. You must repeat this first coordinate that you listed, so that when you do the next step, you actually connect this. You can connect this 5, 11 back to the first step, because that's very important. If you do not do this step, the answer that you'll evaluate at the end of this formula will be wrong. So always remember that this is a very common error when we use this algorithm. So yeah. So now that we have our way to list the coordinates down, we can thus draw the laces. So here I have listed the coordinates here.
Wait,
and
so can you say how to like which coordinate to list first? How do you know which coordinate to list first again?
it does not matter what coordinate you list first. I just chose P1. And it does not actually matter even whether it's counterclockwise or clockwise, but the main thing is that you must start from a certain coordinate and you must put the coordinates in order. So that means that if you look back at this figure, so for example, you could start by putting in P5, right? And you could still work it like this. You could work the graph like this, or you can work it like this. It doesn't matter, but you cannot go from like P5 and the next one you list is P3. This is a no-no, and you will get a wrong answer if you do that. So once again, it doesn't matter exactly what direction you go or what coordinate you start from, but you must start from one and you must go in one direction and you must list consecutive vertices. And like I said before, remember to repeat the first one. Is that clear? Okay, I'm gonna go on now. So our next step is to draw the laces once we have a list of coordinates. So we have our list. I started from P1. So we will start from 3 and then draw a lace directly connecting down to 6. Does everyone see this? And then from 5, you go down to 5, 9 to 8, 12 to 11, and then 5 to 4. So this is our first set of laces, the ones that go down. These should be drawn in like a forward slant. And the ones that should go up are backward slants, and it should start from 5. So when we go from 5, we go from 5 to 4, 9 to 6, 12 to 5, 5 to 8, and 3 to 11. So this is what your work should look like. It should be a set of crisscrossing X's. And the different colors actually denote what type of sign that we will be using in our next step. So once we have our lace set down, we will then use the actual formula. Now, this formula does kind of look intimidating at first, but we can just break it down step by step to be able to find out what all of this actually means. So A here represents the area of the figure. 1/2 is a constant, and then our next thing is the absolute value sign. This can be largely ignored as the main component is these sums. So when we mean A1, B2 plus A2, B3 plus all the way down to plus AN, B1, we mean using each of these laces and then multiplying the numbers at both ends. So in this case, A and B would be equivalent to X and Y. So when we say A1, B2 in this case, this would be 3 and then 6 because it's at the end of this downward lace. And then we can go down 5, 5, 9, 8, and then so on. And then for B1, A2, we just follow these upward laces and then multiply the numbers at each ends. You subtract the ones from the upwards facing slants from the ones that are facing downwards. So that means that in this picture, the purple ones have a negative sign while the red ones have a positive sign. So this, if we use our example with the figure earlier, we would say that the area is equal to 1/2 times the absolute value of 3 times 6. You guys see 3 times 6 and plus 5 times 5 plus 9 times 8 plus 12 times 11 plus 5 times 4. That's all of our red laces, and then minus 5 times 4, 9 times 6, 12 times 5, 5 times 8, and 3 times 11. So that's all of our purple laces added up. Now, if you guys evaluate this on a calculator, excluding the two 5 times 4s, because these can cancel, you would figure out that what's inside this absolute value grouping, it turns out to be -60. So you have 1/2 times -60. Obviously, area cannot be negative, so this is why the absolute value comes into play. And this -60 will turn into 60, because absolute value is distance, a number is from 0. What's 1/2 of 60? Well, obviously it's 30. So the area of that figure that we did before is 30. Is everyone clear on that? Are there any questions? Okay, good. We'll basically summarize what we did. So for laces slanting forward, we multiply the corresponding numbers and add, and we'll repeat for backward slants. We then subtract the sum of the backward slants from the sum of the forward slants. We take the absolute value of that and then multiply that by 1/2 to get our final answer. So with the algorithm out of the way, we can actually try to verify this with that square that we did before. So like before, we would use our list of coordinates, and then we will draw laces, both up and down. And we would evaluate. So here is 1/2 times 5 times 4 plus -4 times -5 plus -4 times -5 plus 5 times 4 minus 4 times -4 minus 4 times -4 again, and then minus 2 times 5 times -5. So this would sum up to 1/2 of 162, which is equivalent to 81. So this is just showing that it works for almost every single polygon there is, and this is just an example. So now I will just introduce the formal formula, which is called the shoelace formula. So suppose the polygon P has vertices x1, y1, x2, y2, and all the way down to xn, yn listed in order. Then the area A of P is 1/2 of the sum of from I equals 1 to n minus 1 of xi, yi plus 1. And then this is meant to connect it to the last coordinate on the list to the first, and then minus the sum of the upward slants. This is the sum of the upward slants, and then this is that upper slant that connects the bottom, the one that you listed last to the one that you listed at the beginning. So this is just another way to write it, but this one is obviously easier to memorize. So a cool trick about this formula is that it finds the area of any polygon if you are given the coordinates of each vertex. That can be very useful in contest problems when you want a coordinate dash, and the only thing that you basically have are coordinates and side lengths. This can give you the area, which is also useful for finding other side lengths and angles. So this formula is also known as the shoelace algorithm due to the nature of the formula having to take several steps. Gauss's area formula, or the surveyor's formula, because a surveyor is a person who maps out land. And this is a useful trick if you have established like the boundary points to be able to find the area of an enclosed area. This formula was first described by Albert Ludwig Friedrich Meister in 1769, and it was verified by Gauss in 1795. So his name was one of the namesakes for this formula. So our next discussion is to basically prove this formula for a triangle. There are other more general proofs of the formula, but a lot of these are way too complicated for the scope of this course. It can go into calculus and it can go to other fields that we will not discuss about. So imagine a triangle has 3 vertices, x1, y1, x2, y2, and x3, y3, and a coordinate plane. Let us denote this triangle as triangle A. So here A represents the area. So we will then start to construct a rectangle, or that basically almost inscribes the triangle in it. So that means that from the leftmost vertex, you draw a line parallel to the y-axis. From the topmost, you draw a horizontal one. And then from the rightmost, you draw ones that are parallel respect to the 2 axes. And this will form a rectangle. When we draw this, it would partition the inside into 4 triangles, one of which is A, but we'll have 3 other right triangles, which we will denote by C, D, and E. Remember that all of these are right. So let's say the area of this rectangle is R. Because A is a part of R, we know that A is R minus C minus D minus E. Now, the thing that we have to do next is to express each of these quantities in these equations, excluding A, in terms of the coordinates of the 3 vertices, which is not very hard because all of these involve right angles, so they're very direct applications of areas by side lengths, which are also easy to find. So what we'll do next is express these. So with R, we know that the length of R is x3 minus x2, which is basically this length that I've drawn in purple here. Does everyone see that? And the height of R is y1 minus y3, which is this length. There's y1's here and y3's here. We will then expand these 2 to create x3 y1 plus x2 y3 minus x3 y3 and then minus x2 y1.
Came into my room just to fart and then left. It smells so bad.
Hello? Please mute yourself. Please mute yourself. Thank you. We can do the same for the 3 right triangles as well. So for negative C, this is just adding the basically negative value of the area of C. This is essentially the same thing as taking out the area of C. We would have 1/2, because it's the area of a triangle, times x2 minus x2 times y2 minus y3. This is due to, once again, the x3 minus x2 is the length, is the horizontal leg length, and then y2 minus y3 is the vertical leg lengths. We'll then expand it again, and we'll repeat for D and E. So at the end, we get a set of 4 terms or expressions, and we will then add it up in order to find out what A is. So we will figure out that A is equal to 1/2 of x2 minus y3 minus x3 minus y2, then minus x1 y3 plus x3 y1 plus x1 y2 minus x2 y1. This might seem like a big jump, but it's all due to simplifying and canceling terms. So if we go back to our previous slide, we can just find each of these terms. So the one that isn't actually denoted by 1/2 is the terms that are in the expression for the area of R. So we have x3, y1, x2, y3, x3, y3, and x2, y1. And we can actually find each of these terms in something that's being taken out when we're taking out the areas of C, D, and E. So for example, when we talk about x3, y1, there's a minus 1/2 of x3, y1 here. If we're talking about x2, y3, we have minus 1/2 of x2, y3 here. x3, y3 has a plus 1/2 x3, y3, so these actually cancel out. And then x2, y1 has a plus 1/2 of x2, y1, so you'll have a minus 1/2 of x2, y1. For all the terms that actually are just the two coordinates of the same vertex being multiplied together, they actually all cancel out. So for x2, y2, they cancel out here and here. x1, y1 cancels out here and here. So what you have left is just the groupings of 1/2 of each of these 6. So we will then rearrange this as here, and then we can just rearrange this to form what's basically the Shoelace formula, just expressed in a different way. So you'll have A equals 1/2 of x1, y2 plus x2, y3 minus plus x3, y1 minus x2, y1 minus x3, y2 minus x1, y3. So this, even though it doesn't have the absolute value sign, that's basically inferred because area must always be positive, and then the 1/2 was just carried there all along. A more rigorous way to put in the absolute value sign is to express this difference as the determinant of a matrix, because it actually does line out, it does check out with that. But again, that's beyond the scope of our course, and this is the basic formula for the Shoelace formula, and it can just be reasonably inferred that the absolute value sign has to be in there. So a beautiful thing about the Shoelace formula is that it seems extremely simple. The algorithm itself is not very difficult, but it can be generalized into so many different things. And this interlocking laces thing is, in my opinion, it's kind of beautiful in some way. This interlocking laces obviously looks like shoelaces, like the picture I put in here. And I think it's a beautiful application and simplification of analytic geometry. So now I'll just ask you guys to do this example problem. This is a problem that does apply the Shoelace formula as part of its steps. So in right triangle ABC, we have angle ACB to be 90 degrees. We know AC is equal to 2 and BC is equal to 3. Medians AD and BE are drawn to sides BC and AC respectively. For those who do not know what a median is a side length that goes from one vertex to the opposite side, but it runs through the midpoint of the opposite side. So when we say the median of AD, we mean that the line runs through vertex A and it goes through D, which is the midpoint of BC. And then the same thing can be said about BE, and as it intersects AC. So we know AD and BE intersect themselves at point F. What's the area of triangle ABF? I'll give you guys about 5 minutes to solve this problem. And if you're done early, you can put your answers in the chat.
Give them 10 minutes. Give them 10 minutes. 10分钟哈。
Do you guys need more time? Okay, since I have some answers, I'll discuss the solution to you guys. So the answer is 1, actually. The area of triangle ABF is 1. So how did we get here? Well, first, we have to figure out where F is on the graph. So to do this, since we know that F is the intersection of AD and BE, let's start by defining what lines are they. So for AD, we can say y is equal to negative 4/3 of x plus 2. Where did we get this? Well, obviously this is point slope. This is slope intersect form. So we know that the y-intercept is at A. So the y-intercept must be 2. And we know that the x-intercept is 1.5. So we know that while the y value goes down by 2, we know that the x value goes right by 1.5. So our slope is -2 divided by 1.5, which is the same thing as -4 divided by 3. For BE, we can do the same thing. So we have y is equal to -1/3 of x. So this is because E is located 1 above the origin. So while E goes down 1, the x value goes right by 3. So that's a slope of -1/3. And then we plus 1 because the y-intercept of BE is 1. So in order to find out what the coordinates of F are, all we have to do is set these two equations equally to each other to find where the intersection is. So we have -4/3 of x plus 2 is equal to -1/3 of x plus 1. Sorry for the bad handwriting, but we then get, we can just move -1/3 to here and 1 here, or you can do it the other way around. You can do 4/3, it doesn't matter. But in this case, we get -x because -4/3 plus 1/3 is equal to -3/3. So that's the same thing as -1. This is equal to 1 minus 2. What's 1 minus 2? That's obviously -1. So we have -x is equal to -1. So we know that x is equal to 1. Now, since we know what the x coordinate is, we could just substitute it into one of these equations. Let's go with the equation for BE for the sake of simplicity. So if we do it there, we get y is equal to -1/3 plus 1. So that means that y is equal to 2/3. So we know that point F has a coordinate of 1 2/3. We already know obviously what A and B are. A is 0, 2, and then B is 3, 0. So we know what these two are, and then we figure out what the third one is. So that's all 3 vertices of this triangle covered. So we can just use this Shoelace formula to evaluate the areas. So once again, these are our 3 coordinates that we're concerned about. We can draw the laces here like so, and then all we have to do is just apply the formula. So we would write A is equal to 1/2 times the absolute value of 0 times 2/3. So what's 0 times 2/3 is equal to 0. Then plus, what's 1 times 0? 0. What's 3 times 2? 6. So that's all the things we're adding. And then we're going to go into the area, into the parts that we're taking out. So we have 1 times 2, which is equal to 2. And then we have minus 3 times 2/3. 3 times 2/3 is equal to 2. So we have minus 2 again. And then our last thing we have to take out is 0 times 0, which is 0. So obviously we can just ignore all these zeros because they just do not do anything to the addition or the subtraction. So what's important is this middle part, which is 6 minus 2 minus 2. So what's 6 minus 2 minus 2? That's 2. So we have 1/2 times the absolute value of 2. Now the absolute value of 2 is obviously 2 itself. So this expression should equal to 1. So this is why the area of triangle ABF is 1. Are there any questions or concerns? If you have any, please just state out loud or put it in the chat. Online, you can find many problems that are similar to this. And there are a lot of problems that actually use the shoelace formula in some way or another, because it's such an important tool to convert something from analytic geometry into this pure geometry. I hope this workshop helps you understand something better or eventually helps you in your future math career. This has been a fun math workshop. Be sure to stay tuned for next week, where we'll discuss pi, or the principle of inclusion or exclusion. Until then, this is Jerry Liu, and thank you for attending this workshop. So, if you have any questions, you can ask now. If not, I guess I'll see you later.